Thank you for joining session 4 of our 6-part Open-NFP summer webinar series. Today, Dinan Gunawardena and Jakub Kaczynski are going to present on the topic of P4, eBPF, and Linux TC Offload. This webinar will describe the mechanisms of utilizing the eBPF language to perform hardware-accelerated network packet manipulation and filtering. A copy of the presentation, archive replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the OpenNFP.org website. Dinan Gunawardena is a software director running the driver team at Netronome. Previously, Dinan founded a software startup and was a senior research engineer with the operating systems and networking group at Microsoft Research for 12 years, shipping technology in several versions of Microsoft Windows and the Bing search engine. Dinan has received over 20 patents and is a chartered software engineer. He has a master's in computer science from University of Cambridge and an MBA from WBS. Jakub Kaczynski is a software engineer at Netronome, specializing in the Linux kernel drivers for Netronome SmartNICs. Jakub is also a researcher with Linux kernel expertise and experience in application development on complex multi-CPU and FPGA platforms. He's interested in high-performance software exploiting hardware capabilities and is passionate about networking. Jakub has a master's in computer science from Gdańsk University of Technology. A little about Open-NFP before I turn it over to today's presenters. Open-NFP's objective is to support and grow reusable applied research in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open-vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems, and direct support from our engineers in the research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 20+ universities and companies working directly with Open-NFP through projects. Thank you, and take it away.
Thank you. So I am going to give you a quick overview of the agenda for the session. We'll start with an intro with the high-level objectives. Then we'll go into some of the details of the high-level model that we have for offloading P4 and eBPF, including talking a little bit about how the programmer model can be made transparent for these offloads. Then we'll cover a brief foray into the infrastructure that we have and the state-of-the-art in the Linux kernel for offloading eBPF programs, covering interesting topics such as the Traffic Classifier, XDP, and also looking at the way that eBPF is translated to popular architectures. In passing, we'll talk a little bit about the architecture of the Netronome SmartNIC and how this facilitates the offload that we are implementing. And then we'll deep dive into the implementation of our eBPF mechanism in the Netronome SmartNIC, followed by a live demo, and then we'll wrap up with summary and questions. So the key objectives are to understand how eBPF is relevant to P4 and really look at the current offload support and the state-of-the-art in the Linux kernel. As we dive into the code, we'll understand a little bit about the structure of an eBPF program and also learn how that is translated and executed in hardware. And then we'll hopefully learn a little bit about the Netronome SmartNIC architecture and how this is applicable to this programmable offload. So moving on to the overview, the high-level model for the offload. Firstly, we should just have a brief introduction as to what P4 and eBPF are used for, and we would consider that these are domain-specific languages for specifying how network components should be forwarding data in the data plane. P4, as we know, is programming protocol independent packet processors, and that has constructs such as descriptions of header formats, finite state machines that are parse graphs, tuples of keys and actions, which are tables, and those actions manipulate the packet header and metadata in packets flowing through the system. P4 includes a control flow, and essentially this is an imperative program which describes the sequence of data-dependent match and actions to take on packets being processed. eBPF, or Extended Berkeley Packet Filters, comes from the popular, it's an extension and an evolution of the popular Berkeley packet filter language that anybody who's used TCP dump will be familiar with. eBPF implements a low-level machine code-like language, which we execute in a virtual machine, and by that I mean virtual machine in strict terms of an execution environment that has restricted memory. In this case, has no sleeps and locks, and a very limited API to the kernel. The virtual machine is executed in the Linux kernel, in the Traffic Classifier subcomponent, as we'll talk about later. Code is injected into various hook points in the kernel data plane, allowing us to actually process packets as they come in and out of the kernel stack. We have in eBPF maps, which are essentially key value stores, which can be shared between user mode processes and the kernel. And we have these filter functions which can be chained together, which allow us to have multiple actions that can be operated over the same packet. We have the concept of match actions, as before, as we've seen from P4. And one of the key facilities of eBPF is the static verification of the code that the user tries to execute to basically verify that the code is safe to execute. It has guarantees that it's going to terminate and so forth. And this is obviously beneficial when you allow the user to inject arbitrary code into the kernel data path. We want to ensure that we don't stall the kernel or cause any other errors to occur. So how can we get from P4 to eBPF? And hopefully from the previous slide you can see that there were a lot of constructs and concepts in P4 and eBPF that seem quite equivalent. And in fact, this is the mechanism that we use to get from P4 to eBPF. So John Fasterbend has written a compiler that will take a P4 program and convert it into eBPF. Now, the eBPF representation that we're talking about here essentially looks like a traditional C program, uses C syntax. So if you have a construct in P4, such as the header type, that maps into the struct in C in the translation. If you take another one like the parser state or an action body, those map to a code block. Table apply in P4 would be implemented using a switch statement in this translation. So what John's compiler does is it takes a P4, converts it into this C-like representation, which is then put through Clang, the LLVM backend, spitting out eBPF bytecode. So you can see with the Venn diagram on the bottom right that there's an overlap between the functionality of eBPF, which in fact can do a lot more than just packet processing. It can be used for putting tracing and probes into the kernel, accessing kernel data structures, which may have nothing to do with packet processing. But the key takeaway here is that the scope of the compiler that John's written is purely in the area of packet filtering and simple forwarding. It's not meant to be a complete translation between all the functionality of eBPF and P4. So we mentioned earlier that it's very nice to have what we call a transparent offload model. And what this means is we're talking about having code that could be run in the kernel or in hardware. That's what we want to do with the eBPF program. We want to facilitate the mechanism to offload it into hardware. And for this to work, you have to have a number of requirements met. And this includes being able to have part of a pipeline, part of a sequence of eBPF programs offloaded. So if you look at the diagram at the bottom with essentially a packet coming into the system, in this case it passes into eBPF program 1, which we mark hardware offloaded. If that packet is then forwarded on outside of the eBPF program 1 to program 2, which is also hardware offloaded, then we have managed to get the processing done in hardware. But here we have a third program which, for whatever reason, cannot be run in the hardware. So that runs in the kernel mode, in software. And at that point, the packet that's being processed has to cross the PCI Express bus. So we try and keep the packet within the network interface card domain for as long as possible. So the requirement here is being able to do a partial pipeline offload, but also ensuring that there's a fallback path to software for any eBPF code that we choose not to offload into hardware. And we also need to be able to handle the maps or the tables in a transparent way so that accesses from user mode or kernel mode can be represented correctly in the hardware and vice versa. So now we'll have a quick look at the kernel infrastructure for eBPF offload. So the main component in the stack that allows us to do eBPF offload is the Linux Traffic Classifier, the TC. And this does a multitude of, implements a multitude of functionality. Classic traffic classifier and shaping operations, scheduling packets in FIFO fashions, for instance, policing packets that exceed a bandwidth guarantee, dropping packets, those kind of things, and maybe marking packets. And you can see at the bottom there's a diagram which it's actually has more detail than we probably want here, because what we want to show here is that essentially packets come in through an ingress port, get processed in the middle by the TC and the network stack, and then probably goes out of another port, an egress port. And you can see the points at which the eBPF program can hook in there and run within the traffic classifier. So what kind of program are we talking about? So if you look in the top right, we have an example of a simple program that you might want to implement using this infrastructure. So in this case, a packet comes in at the top. It hits this decision point where we check, is this 802.1 Q VLAN tag packet? And if it is, we go down the right-hand branch where we pop the VLAN tag off, and then we recirculate and reclassify this packet through the same program. At this point, we find that the VLAN tag is not there, so we go down the left-hand decision branch. We check whether the packet is IPv4. If it is, we're then looking to see if it has that specific IP address of 10.0.0.21. If it does, then we choose to drop the packet, and that packet is not forwarded any further. If it doesn't, then we are checking if it's part of the 10.0.0.0/24 subnet, and if it is, we do the set QMAP, and then pass the packet on for further processing for any other chain filters. Another mechanism in the kernel for executing eBPF is the Express Data Path Protocol, XDP, and this comes from our colleagues at Facebook, Tom Herbert, Alexei Starovoyshov. And what this is it's a high-performance programmable network data path. So it's there to do many of the things that you'd like to do with eBPF and packet processing, doing forwarding or load balancing, or looking at packets, arrival rates to mitigate denial of service attacks, or just implement basic firewalls. And the key thing here with XDP is XDP sits underneath the TC in Linux. So we're getting closer and closer to the hardware. And the advantage of running the eBPF filter closer to the hardware is that we have the option to process and potentially drop a packet earlier in the data processing pipeline as it's received, which leaves resources further up the stack free to do other things. So before we dive into details of our implementation, it's useful to understand a little bit about the architecture of the Netronome SmartNIC and how this plays into our implementation choices. So the Netronome SmartNIC essentially has packets coming into the system through either a MAC or a PCI Express interface, and then those packets go to a sea of workers or microengines that have associated with them memories which are close and fast to them, which allow packet header and metadata to be held very close to the processing points within the microengines. But we have larger memories which may be further away that can store the packet data and payload, which can be accessed if need be. The philosophy here is to try and bring the essential data as close to the processing point as possible. Within the microengines, we have mechanisms to allow us to do highly concurrent access to memories and to mitigate the latency and costs of doing branches, accessing I/O, and memory, allowing us to have multiple threads executing within the microengines. So let's start getting to the nub of this. How do we make an eBPF program and get it to run in the hardware? So essentially, we start by writing our program, which may be a P4 program, which is then translated into this eBPF C representation, or we can start by writing it in eBPF C. We then compile that to eBPF bytecode, and we load it into the Linux TC. When this gets loaded into the Linux TC, it's run through the static verifier to check the safety guarantees and whether the functionality in that eBPF program is supported by the TC. And then, if it is cross-compiled to the appropriate target architecture, and that might be x86, which would allow you to run it on the host CPU, or, in our case, into the bytecode for our Netronome SmartNIC. So let's talk a little bit about the data flow and how this works. So we get packets coming in from the network, and that arrives in our firmware and hardware, and that gets passed across a PCI Express bus as packet plus their descriptor and associated metadata. The first point is it hits the inside the kernel is it hits the driver, which is where the XDP protocol would live, and that allows the eBPF program, if it's implemented in XDP, to process the packets before we create the SK buff and send it on to the traffic classifier. The traffic classifier then gets a chance to have a look at the packets and pass them through its processing pipeline, and then the packet will be sent on to the TCP stack and ultimately onto any user mode application, perhaps via a socket. So when we run the eBPF script in our firmware and hardware, which actions within eBPF do we support? So in effect, the first one we support is drop. So you can see that with the X at the bottom. So a packet comes in, it runs through the eBPF script on the hardware, and we might choose to drop it. So that in the prior example, that might be the case where it matches that specific IP address in a blacklist. The next operation we support, next action we support, is to redirect. So we might receive this frame and decide that we actually just want to send it out another port. So that would allow us to redirect before it has to be sent any further up the stack. And then the third action that we support is to mark, and that would be adding some fields into the metadata, for instance, and passing the packet further up the stack for subsequent processing. So now I'll hand over to Jakob, who will talk about the specifics of our implementation of eBPF in the Netronome SmartNIC.
Thank you. So let me start by explaining the diagram a little bit. In this diagram, we see the Linux Kernel Networking processing stack on the right-hand side. And on the left-hand side, the orange box is the eBPF program, which is handed from the user space to the TC, to the Traffic Classifier, interpreted or compiled there to the host architecture today, and run for incoming and outgoing packets. And we extended the user space API to also be able to pass on some flags. And the flags are specified per program, and they allow fine-grained control over the offload. So user can specify that a given program is not supposed to be offloaded to the hardware, or he wants the program to be offloaded to the hardware, and if it's not possible, an error should be returned. If no flags are specified, the offload is done fully transparently. That is, the program is handed to the Traffic Classifier, and if offload is possible, it will happen, and the program will be running the hardware. And if the offload is not possible, the Traffic Classifier will handle the running the program. Apart from adding the flags, we added the entire path on the left-hand side. That is, when the Traffic Classifier gets the program and the optional flags, it will pack the program with some metadata and internal information into what we call an offload object, and that object is handed to the driver. And if driver can perform the offload, it will accept the offload object and perform the offload, and other drivers, basically all drivers apart from Netronome drivers today, would just reject that offload, and the Traffic Classifier will handle the classification by itself. So if the driver is capable, it accepts the offload object. It will then perform translation of the program into something that the hardware can understand, and program and reconfigure the hardware so that the classification and the handling of the and execution of the program can happen in hardware. One more thing on this diagram. As you can see, there is a blue arrow which shows stats coming back from the hardware into Traffic Classifier. It's important to note that the offload we are performing must be transparent. That is, the user space should not be able to determine whether the program is running in the hardware or in software without performing some sort of system calls. So the behavior should be completely identical between the offloaded and non-offloaded case. So because of that, we need to populate all the statistics and all the information inside Traffic Classifier, which would be gathered if the program was run there. So therefore, the blue arrow showing that we communicate the stats and all the necessary information back to Traffic Classifier from the data path running in the hardware. I will now explain slightly more in detail the translation itself. On the left-hand side, we can see the eBPF registers. The eBPF machine has 10 64-bit registers, which is defined. The registers are defined as 64-bit to match modern host architectures easily for the translation to modern host architectures to be easy. The NFP on the right-hand side has two banks of general-purpose registers. There are 16 registers in each bank, and the registers are 32-bit. And the NFP has some communication registers and some special-purpose registers as well. So when we perform the translation of eBPF to NFP machine code, we must allocate the 64-bit registers into two 64-bit parts in the A and B banks for each 64-bit registers, and we also can perform some allocation of data which we know will be used in a specific way to the communication registers. The communication registers can be thought of as explicitly controlled cache on the host systems. When the user accesses on a host system, when user is accessing DRAM memory or I/O devices, the accesses are done through L3, L2, and L1 cache. On the NFP, we don't have the processing engines don't have communication registers, which are basically used to fetch the memory, to fetch the data from the memory, but they are controlled by the software and not allocated automatically, which is usual for real-time processors and processors which have to run at low latency. The last piece of the puzzle is translating the maps. Maps in eBPF are basically hash tables. On the right-hand side, we have a diagram here showing the usual setup for using maps in the kernel today. There's usually the map and the data resides in kernel memory, and there's usually a user space control application associated with it, which can use system calls to read and write that map. But the map is accessed mostly by eBPF programs running in the kernel, and those programs can read and write the map as well. So if we want to offload eBPF programs which make use of maps, we have to make sure that the map is available both on the host and in the host and on the NFP memory. If we wanted to use the host copy from the NFP, it would be too slow across the PCI bus to fetch information from the map is not acceptable, unfortunately. So on the bottom left, in the bottom left corner, I specified the four most basic use cases and configurations of maps. I will now go through them. The easiest use case to support is that the eBPF program is using the map in a read-only mode. That is, the user space control application is writing the values into the map, and the eBPF program is only reading them. And it's effectively similar to what routing routers do today, which is basically there's a control plane which is populating the tables, and then the processing path is only reading those tables. And if there's only a single user, and if the BPF program is the only user of the map, it's fairly straightforward to support. We have to just add a hook point in the map write path in the kernel and reflect all the writes into the hardware so that the hardware have a consistent copy of the map for its use. The same for multi-user maps. That is, the maps are still only populated from user space, but there are other BPF programs reading them in the kernel. So that, as an example here, we could have two programs, one being offloaded to the hardware, and that would be our fast path, and then we would have another program running in the kernel, and they can both read the maps, but the reflection is still sufficient to make sure that the view of the maps is consistent. The problems start to arise when we try to enforce coherency with writes both on the device and in the host memory. So we can still support a use case where the eBPF program is the only user of the map, but and it wants to write values to the map. Effectively, what we do in this case is make sure that there's our offloaded eBPF program is the only program using the map, and we do that by assigning a specific ownership value in the Linux kernel stack to the map and associating it with our network device, or a specific network device, and that will make the Linux kernel stack reject other programs from binding to the same map. And then if the control application wants to read the map values, we will just provide the values from the card instead of the kernel copy. But if we try to do writes both in the kernel and in the device, this becomes a little bit of a problem, because if values can be changed or added both in the kernel space and on the device, ensuring consistency and synchronization between the both copies makes the performance suffer. So a few words about optimizations which we have done or are planning to do during the translation. First of all, the NFP has a lot richer memory architecture than standard x86 or standard server CPUs. So we can make sure we allocate the data and the maps appropriately to memories with different latency and performance characteristics. And we can accelerate some of the memory operations by using our memory engines. We also perform some simple people optimizations, like optimizing the jumps if they are optimizing them out if they are unnecessary, performing some of the loading some of the immediate values directly into the instructions, which is not always possible in eBPF. We can also, eBPF has slightly limited constrained instruction set to match all the host CPUs that it can run on. So the NFP can perform some of the operations in a single instructions, some of the operations which eBPF would take more than one instruction. So we perform a simple optimization of and try to fuse those instructions into a single one. And the biggest piece of the optimizations and the translation come from the fact that NFP has 32-bit registers, and that forces us to perform a liveness analysis and track the size of the elements which are stored in the registers, and that allows us to also track dependencies between the registers and then allocate the registers to A and B banks in the NFP. We'll now show a simple demo of a program performing filtering of TCP flows. We have a statistics set up on the left-hand side. The statistics, the first section will show statistics of TC. The second section is interface statistics for the interface, for the NFP interface, and the last section is hardware statistics read directly from the card. This terminal will show the kernel logs. Okay. I will enable the TC offload globally now, and load a eBPF, enable TC on ingress, and load a eBPF. Oh, sorry. First, I should probably start by showing the program which will run. So this is a simple application, a simple program written in C. This is the entry point. We get what is a slimmed down version of the Linux kernel SKWAF and we perform basic parsing of the packet. So we start with layer 2, we check if the packet has VLANs or not. If it has a VLAN tag, we will strip the VLAN tag, and we'll go on to parse the IP header, IPv4 or IPv6. We then parse the IPv6 or IPv4 and come on to TCP header finally. And if we got to the TCP header, we'll check if the destination port is port number 58. If it's not a TCP packet or the port is not 58, we will just let the packet through and we will drop all the packets coming to port 58. So this is our application. I will now compile it using Clang. So as we can see here, I'm invoking Clang, the Clang the C compiler, the Clang C front end, including some eBPF headers. We'll emit LLVM data, and then LLVM backend invoked right here will produce BPF bytecode. So we'll do that. We can see that we have the object file here. We will now load it. We will now add this to the. We'll now load this into TC. I will first show the non-offloaded case. So I'll make use of one of the flags that we added. I will specify here that we want to skip hardware. That means that the hardware offload will not be attempted. We can see on the left-hand side the statistics got updated, and we have the filter statistics, the TC filter statistics now in the first section. I can generate some traffic now, just perform a simple thing. We can see the statistics for the interface and just receive and transmit statistics on the interface incrementing. And I will now generate TCP traffic, simple send TCP packets which are destined to the port 58. So this should be dropped, and it gets dropped. As we see, we have no responses, and the filter on the left, we can see that the filter matched, which means the drop action was performed for 10 packets and 990 bytes. And now I will remove the filter and load it into the NFP. So I will not specify any flags now for the offload, which means that the transparent offload should take place. And as we can see in this window, these are the kernel logs. Our driver printed a simple message, debug message, telling us that the code was reloaded, the eBPF code was compiled, and it took 140 NFP instructions to implement that filter. And the logs that we see now showing up every second are polls of the statistics. So the messages that are coming in is our driver reporting the statistics from the data path into the kernel side. So similarly to the previous case, I'll just send ping now. And as we can see, not only on the left, starting from the hardware statistics, not only are the transmit and receive statistics incremented, but also the BPF hardware statistics for pass getting incremented. So if we send more traffic, you can see that the standard ping is passing. And statistics for interface are incremented as well, but the statistics for the filter are not, because obviously the ping is not matching our filter. But if I generate TCP traffic now, we can see the up one counters being incremented. These are the counters in this case which are counting drop packets. They are called up one because the meaning of the counters is specific to depends on the action which we are performing. As Dinan have said, we can perform mark action as well as redirection and drops. So the meaning of the counters depends on what program is compiled. In this case, we are using up1 for drops. And let me run the traffic again. We can see that the drop hardware drop statistics are incremented, and we can also see that the TC statistics on the top are incremented as well. We can see that TC reports to the user space that 30 packets have been dropped by this filter, and the appropriate number of bytes have been dropped as well.
Particularly there, the interface stats didn't.
Yes, and we can also see that when we are sending the TCP traffic, the interface stats are not being incremented right now. This is something that we are discussing with the kernel community. We have to decide whether the transparent offload should mean that the interface statistics are incremented because the packets did hit the physical port of the card, or should they not be incremented because the packets never reach the kernel data path. So right now our implementation does not increment the interface statistics, but as we can see, but this is still to be decided whether this is going to be the final design.
Okay. So, in summary, what we've learned hopefully in this seminar is about the relationship between P4 and eBPF and how we can translate from a P4 program into eBPF. Further, how the Linux kernel infrastructure has been augmented to support the execution of eBPF programs within the stack, and also how we extended that infrastructure to allow the eBPF programs to be offloaded into hardware. We learned a little bit about the Netronome SmartNIC architecture and how that's optimized for network flow processing, and then dived into how we implemented the eBPF offload hardware and some of the clever optimizations that were necessary to make this work. And with that, we'll switch over to questions. Thank you very much.
Okay, so let us take the questions now.
So the question is, why did the hardware stats increment when you did skip hardware?
Okay, so the hardware, can we switch back to the demo? How do I? The hardware stats, there were two sets of statistics, maybe that was not clear. The first bunch is statistics for the port. So the first four statistics are just the port statistics, which I include to show that the data is actually flowing in. These are not the BPF statistics. So if I did, let me just quickly load, skip hardware again. If I'm running in this mode, we can see that only the first two statistics are incremented, right? So these are only the statistics that are reported basically by the MAC saying that there is data flow. The statistics that are associated with BPF are the latter ones, the BPF pass and the BPF application counters, and they are not incremented, as I can quickly show again. Let's just add with no flags. And then we can see that both those statistics and the statistics for the app are incremented.
Okay, thank you. The next question was, what kind of information would be possible or impossible to store in the maps? And I think the key thing here is the maps are of the key value stores?
Yes, the maps are completely arbitrary. So the user space application is writing the map values, and it's also like it is expected that the user is both writing the control application and the eBPF data bus program. So it's entirely at user's discretion to design the data format there, and the user can store whatever information he wants in the maps, and then pass populate the maps with whatever information he chooses. One of the things, for instance, one of the challenges here are that the user is populating the maps with the data which can be Linux specific. So, for instance, if user is writing IF index, which is the networking interface index, into the map and then retrieving it in the BPF, we have no way of interpreting that before we load the program. So we just have to make sure that there is a translation on the card between the Linux interface indexes and the ports on the card. So yeah, the maps are completely arbitrary.
Yeah, although obviously the amount of memory, the size of the maps is important as well. We're going to mirror that down further down the stack.
Yeah.
So it sort of leads into answering the next question, which is, are we able to hold arbitrary dynamic state using the maps? And I think really that is the point of the maps. The maps can be modified from user mode or the kernel mode, or within the hardware. Of course, when we do it from within the hardware, we have to deal with this coherency problem.
So yes, the only problem that we can have is coherency if the map can be modified both from the kernel and on the device, but we can really provide any sort of access and store any information in the map.
I think there weren't any other questions that weren't answered, so we'll hand back to Brian.
Thank you, guys, and well done with the webinar today. I'd like to remind everyone that the replay, as well as the slides and any project code, will be made available shortly after. And we look forward to having you join us on our next webinar on September 7th, Protecting the Privacy of the Network Using P4 to Prototype and Extend Network Protocols by Mark Matisse from the Johns Hopkins University Applied Physics Lab. Until then, thank you very much for your time.